Well, hello everybody. This is Bill Johnson. I'm working with Eddie Pazmiño to provide particle transport and surface interaction software called PARTI-SUITE. If you're seeing this, you've probably found the website and obtained this video from there. This video concerns extended DLVO interactions. So once you've downloaded the extended xDLVO module, when you open it, of course, you need to right-click and run as an administrator. If you don't do that, it will pretend to run, but it won't do what we want it to do, and I'm not sure what it will do, in fact. I just know that it won't work, so make sure that you right-click and run as an administrator. And at first, it'll bring out a command window, but then it will open up a GUI, graphical user interface. So once the GUI is open, maximize that screen so all the parameters show correctly. And so this graphical user interface, it's kind of intimidating in terms of the number of parameters to begin with, but it's quite versatile. And so I'm going to run you through those real quick. So the conventional parameters for mean field DLVO theory are shown here on the upper left. And obvious values for temperature, the ionic strength of the solution, the colloid radius, collector radius. Now note that there are different geometries. You can do sphere-sphere or sphere-plate. And so I'm just going to show you this for sphere-sphere. The colloid zeta potential, the collector zeta potential, the valence of the symmetric electrolyte, the relative permittivity of water, the van der Waals characteristic wavelength, and the Born collision diameter. Okay, so those are all corresponding to conventional classic DLVO theory, but we also have the extended DLVO parameters here, below that, the Lewis acid-base decay length, the steric decay length, and then the steric energy at minimum separation distance, and for roughness, the asperity height above the mean surface. Now, roughness has multiple geometries. You can do non-rough smooth surface. You can do rough colloid and rough collector. You can do both. Okay. Now, when you do both, the value of input here is assumed to be the same for both, and the default value is 10 nanometers. A number of studies have shown that the nature of roughness is that smaller asperities are superimposed on larger asperities, and that the reduction in the interactions, whether cast as forces or energies, decreases with the addition of asperities, but non-monotonically, so that asperities increasing in size from a few to a couple tens of nanometers have their largest effect, that is, produce the greatest decrease in the interactions. And then as asperities increase in size from a couple tens of nanometers to larger sizes, those impacts decrease. And that impact, or that effect, is well described in Rasmussen et al. 2019 and in the references cited therein. I think that's enough said about that, other than the roughness solely decreases interactions. It does not flip a repulsive interaction to an attractive interaction. And so you cannot explain adhesion through roughness alone, other than to increase the number of contact points made by the colloid and the collector surface, which undoubtedly plays a role and is not well parameterized yet. However, there is evidence that charge heterogeneity also plays a major role, because we know that the ionic strength has a significant impact on attractive and repulsive interactions under unfavorable conditions. And so charge heterogeneity is an important aspect that I'm going to go through here that's independent of roughness. And in fact, that independence, or that independent effect is demonstrated in different roughness approaches. For example, Torxabon and Bradford introduce roughness in their calculations. They use pillars to represent the roughness, which is a different approach than that approach used here, where we think of the roughness as contiguous asperities, and so we represent them as hemispheres on these surfaces. And so in their system, which are pillars, the surface coverage needs to be specified, where in our system it's implicit. These features are contiguous. But notably, in their work examining the impacts of roughness, they did place attractive zones at the tops of the pillars, effectively surface charge heterogeneity at the tops of the pillars, because you need that in order to explain adhesion to rough surfaces, albeit with the caveat that there's also these important impacts of multiple points of contact. Changyang Shen in China and others have well demonstrated that those multiple points of contact are important players in adhesion. So I think that's enough said about roughness. Other than that, this value that's put into this asperity height is the value that we also use in the trajectory models. And in fact, all these parameters here are designed to allow toggling back and forth between the xDLVO and the mechanistic trajectory simulations to allow that interplay to be explored, And so the fact is that there are two roughness asperity sizes that are input into the trajectory models, one of them corresponding to this one that sets the colloid-collector interactions, but another one, the larger one, that represents the larger asperities responsible for dictating the hydrodynamic slip. But that's not relevant here in extended DLVO simulations. That is a transport issue, and so I don't need to go into that here. But the correspondences between this value here for the asperity height above mean surface corresponds to the smaller asperity size that is input for colloid-collector interactions in the trajectory simulations. Okay, so I think that's enough said about roughness, geometry, basic parameters. Now, one thing that is very useful here is that for these parameters, such as van der Waals, acid base, and adhesion-related parameters, you can calculate these values from fundamentals. So first I'll go to the calculate from fundamentals for the van der Waals. And you can see here that there are Hammacher constant values that you can input. So the main electronic absorption frequency, the colloid dielectric constant, the colloid refractive index, the collector dielectric constant, the collector refractive index, and the fluid dielectric constant and fluid refractive index. And so you can calculate the Hammacher constant for these materials, surfaces interacting with one another across a fluid. The default values are set for polystyrene interacting with glass across water. When you do this calculate button, it calculates the Hammacher constant, joules, and then populates this box, which will be used in the calculations for the xDLVO. Another option is to examine a coded system. So when you calculate from the van der Waals interactions for the coded system, the Hammacher constant now becomes not applicable because you have to develop that representation of the coded system in the calculations. So we don't input that in that box, and instead you input what type of coded system. Okay, so maybe the word layered is more easy to understand. Layered colloid, layered collector, colloid with layered collector, or layered colloid with collector. Okay, and you pick those, and depending on which one is involved, different boxes become active. And so you need to know the coating thickness for the colloid if it has a coating, or the collector if it has a coating. You need to know the fluid Hammacher constant. And then the coded system has the energy, joules, for the combined Hammacher constant values. Now you can input those if you know them directly, or you can calculate those from even deeper fundamentals. Okay, so the single material values for the colloid Hamaker constant, the colloid coating Hamaker constant, the collector Hamaker constant, and the collector coating Hamaker constant. Okay, and likewise, you can do that for each one of these boxes. So you can check all of these calculate from fundamentals if you don't know those values already. So calculate, it calculates the colloid coating, collector coating values down here. You use the calculated values, and that closes the panel. Okay, and those values are now populated all up into here for the utilization in the simulations. Okay. While that panel is open, by the way, you cannot go into these different things won't do anything, even though the checkbox is checking that the panels that correspond to them are not active. So you have to finish with your coded system panel and then move on to these other options. So you can calculate your acid-base energy at minimum separation distance from the fundamentals, and that opens a box with the electron acceptor donor properties for the colloid, collector, and fluid that allow you to calculate that acid-base energy at minimum separation distance. You can also calculate the work of adhesion from the fundamentals using the free energies, van der Waals free energies for the colloid, collector, and fluid. The acid-base energy at minimum separation distance figures into that also, and so but that allows you together to calculate the work of adhesion. And then the contact radius can be calculated also from the fundamentals here with the Young's colloid Young's modulus, collector Young's modulus, colloid Poisson's ratio, and collector Poisson's ratio to get the contact radius from those and the work of adhesion. So calculate that, you get the combined elastic modulus, the contact radius, and that is populated down here. So all these things are ready to use based on the fundamentals. All right, so having done all that, and this is all defaulted to the polystyrene latex interacting with glass across water system, we can do the calculation. So we calculate the profiles for the DLVO interactions, extended DLVO interactions. Notice there's a checkbox here for over the mean field surface and over a heterodomain. And one thing I forgot to mention is you may be wondering, well, why isn't a coded system option involved in the electric double layer parameters that are driven by the zeta potentials? And the reason is that the van der Waals interaction is a volume-based interaction. Those forces extend far enough that the volumes of the particles within a given distance of one another are interacting. Electric double layer, steric, acid base are all surface interactions, and so are not volume-based. And that's why the coded option applies to the volume-based interaction, which is the van der Waals. Now, with respect to mean field surface simply means a surface lacking nanoscale heterogeneity, or the nanoscale heterogeneity is so nano, so fine, that it acts as a mean field surface. The heterodomains, the zones, nanoscale zones of attractive charge, are too small to have a significant influence on the colloid. Okay, so it's a so-called mean field. Okay, so you can think of a mean field as either being monolithic with a single charge as measured by the zeta potential, no heterogeneity, or the heterodomains are too small to have significant impact. So you can plot this over the mean field surface as conventionally done. And so push calculate profiles, two plots will come up, one for the energy in KT and one for the force in newtons. And you have control over both the X and Y axes. It's slightly clunky, but not too bad. And this is just in the GUI. I'll show you in just a second that you have output files that you can manipulate in any way which you'd like. The y-axes are set by simply changing these numbers, setting the positive and negative limits. Okay, so I'll close that plots panel and note that you can set the output directory. It'll default to whatever your system defaults to. Windows System 32, not a great place to be storing stuff. So I'm going to go to my own users directory and just plop it in here and select that folder and save the file. So those calculations are now being saved to an Excel spreadsheet in that directory. So now that that's happened, I want to show you how to load parameters from a previously developed output file so you don't have to go and repopulate all these should you want to reproduce an old simulation. So I push that button to read from an old output file. It's defaulting to Windows and I want it to go to users. Going to that users directory. Now note there's a little bit of a glitch. It's looking for system 32 *.xls rather than just simply .xls. So I've changed it to look for all files, and if you do that, then you can find your output. And so I'm opening that, and now it will replace all the values here, which are the same as they were. Actually, I didn't change anything, but the point is it changed them, and you can see that because our output is actually to higher number of significant digits, and it's populated the GUI with those. Okay, so that's how you input old inputs into your calculations. And in your directory, that Excel file has a lot of information in it. All this input information plus all of the profiles in both energy and force format. Okay. A final aspect that I want to show you is that the option is given to instead plot this over heterodomains. Okay, nanoscale zones of opposite charge to the mean surface. So you input that zeta potential. We typically, by default, simply do the opposite of the measured collector zeta potential. So positive 0.065 volts, 65 millivolts. In this case, now notice that it is also showing you the ZOI radius in meters. That's the zone of interaction, which is finite because of the curvature of the, at least the colloid surface, or if it's a sphere-sphere, both surfaces. And beyond a certain separation distance, as you move away from the closest point between the two, the interactions between them become negligible because of their short distances over which they reach. So the zone of interaction under the conditions provided here, which is 6 millimolar ionic strength for a 4.4 micron diameter colloid, that zone of interaction is 186 nanometers. And so the point is that's our reference because we have to fill a significant fraction of that zone of interaction with a heterodomain to create a net attractive interaction between the two. And so this serves as a guide for how big the heterodomains have to be to have an effect. And so you'll see that it will calculate the size of the heterodomains that fill 25%, 50%, 75%, or 100% of that zone of interaction. Okay, what's the radius of those heterodomains that fill that fraction of the ZOI area? So we hit calculate profiles, and it gives you initially the mean field plots, but then changes to the heterogeneity plots. And what you see is that the mean field value is shown in the black dashed line, but if the heterodomain covers 25% of the zone interaction, here's the net interaction, or if it covers 50% of the interaction, it, in this case, completely eliminates the repulsive barrier. And then beyond that, 75 and 100% filling of the zone of interaction further increases the attractive interaction. You can look at it in terms of force as well. So that's how we look at the heterodomain influence. And when you close that plots panel, these values have been now populated so that to cover 25% of the area of the zone of interaction, one needs a 93 nanometer heterodomain. Or to cover 50% for this set of inputs, one needs 132 nanometer heterodomain. And to cover 75% of it, one of course needs one needs a 161 nanometer heterodomain, And then, of course, to cover the entire 186 nanometer zone of influence, one needs a 186 nanometer heterodomain. So this is intended to allow you to toggle back and forth between determining the interactions between the colloids and the surfaces interacting across your intended fluid, and understanding the scales of heterogeneity for a given ionic strength that will impact the interactions. Notice if we change the ionic strength, so at 6 millimolar for this colloid, this size colloid, the zone of interaction was 186 nanometers. I'm going to change this to 20 millimolar ionic strength, and I'm not even going to change the zeta potentials, even though they would increase in response to that. So let's just do it without that increase. And if I do that, let that stick. So increase it to 20 millimolar, and now calculate the profiles over the heterodomain. And close that plots panel. Now that zone of interaction, just by the ionic strength, even though it's a hypothetical change, because you wouldn't be able to increase ionic strength without increasing the zeta potentials, it's decreased from 186 to 137. Now let's decrease the zeta potentials to something reasonable. So going from 6 to 20 millimolar for this size colloid, we've seen the colloid and collector decrease from 70. So let's knock it down to knock it down to 35. Whoops. But I should make it 3.5. And we'll knock this down to 32. Okay, so we're going to say knock them down by half. Okay, so now I'm going to calculate that again, close that again, and now you see that zone of interaction is the size of it is not impacted by the zeta potentials themselves. The size of the ZOI increases with the square root of the product of the radius of the colloid and the Debye length. And so it decreases with increased ionic strength. And so when we increase the ionic strength from 6 millimolar to 20 millimolar, we decrease the ZOI radius from 186 to 137 nanometers.
And so what's most interesting about this approach with nanoscale heterodomains is that in addition to the rise and fall of the repulsive barrier and the primary minimum with changes in ionic strength, we also expand and contract the zone of interaction with changes in ionic strength, which creates a much more versatile response in the overall interaction with changes in ionic strength, and allows a better match to observations relative to what can be obtained with classic mean field DLVO theory.
So those are the capabilities of this DLVO spreadsheet. Again, it's intended to toggle with the transport simulations. We want you to ask us any questions you might have. Let us know about any bugs or issues, and we hope to hear from you. Thanks.